The water tasted normal. That's what astronaut Chris Hadfield said after taking his first sip aboard the International Space Station. Clean, refreshing, no different from what you'd drink on Earth. But here's what he didn't tell the cameras, what most people never realize. That water, every single drop of it, was yesterday's urine, yesterday's sweat, yesterday's exhaled breath, condensed from the air. It had been inside someone's body, expelled as waste, then captured, processed through filters and purifiers, and transformed back into drinking water. And this isn't some emergency measure or clever science experiment. This is how astronauts survive. Because launching a single liter of water into orbit costs approximately $10,000. And up there, 400 kilometers above everything we've ever known, you either learn to recycle everything or you don't survive long enough to come home. But that recycled water is just the beginning of what people misunderstand about life in space. The reality is far stranger than you've been told. Right now, as you read this, several human beings are falling toward Earth at over 28,000 kilometers per hour. They're plummeting through the void like stones cast from the heavens, dropping toward the planet at speeds that would make a fighter jet seem sluggish. But they will never hit the ground. They'll fall forever, circling the Earth 16 times each day, witnessing 16 sunrises and 16 sunsets, suspended in an eternal ballet between gravity and velocity. This is not science fiction. This is life aboard the International Space Station. And here's the twist that almost nobody grasps. The ISS isn't floating peacefully through space. It's actively dying. Every single day, atmospheric drag, even at 400 kilometers altitude, pulls it slightly closer to a fiery end. Every month, its orbit decays, without constant intervention, without carefully calculated boosts from visiting spacecraft pushing it back up. The largest structure humanity has ever built in space would burn up in Earth's atmosphere within just a few months. The station is falling in more ways than one. Yet through human ingenuity, international cooperation against political tensions and national rivalries, and the relentless work of engineers across 5 space agencies, it continues to soar. Hello there, and welcome. I'm so glad you found your way here. Maybe you had a long day thinking about what's possible. Or maybe you're the kind of person who falls asleep, contemplating how the extraordinary becomes ordinary. Either way, tonight's journey is for you. Let your mind settle, your breathing slow, and prepare to understand something most people never grasp about what it truly means to live in space. Tonight, we're not just learning facts about the International Space Station. We're drifting through its pressurized corridors, understanding what it means to live where up and down become meaningless, where a single mistake could mean catastrophe, where up to 7 human beings currently call home a structure that circles the planet every 90 minutes while simultaneously dying a little more each day. What you'll hear tonight may challenge what you thought you knew about life in orbit. Some revelations might surprise you. Others will gently reshape your understanding of human endurance and ingenuity. And if these calm, curious explorations help you unwind or spark something in your imagination, consider subscribing to help others discover this channel, one sleepy soul at a time. Now let's begin our slow, gentle drift through the remarkable truth of life in orbit. An engineering marvel, built from chaos. The International Space Station began not with careful planning, but with desperation and political necessity. When the Soviet Union collapsed in 1991, Russia inherited an ambitious space program it could no longer afford. The United States, meanwhile, had invested billions in the Freedom Space Station, a project growing more expensive and complex with each congressional review. Both nations faced a choice: abandon decades of work or find an unlikely partnership. They chose partnership. And on November 20th, 1998, a Russian Proton rocket lifted off from Kazakhstan carrying Zarya, meaning sunrise, the first module of what would become the International Space Station. This wasn't a Russian module, though it was built in Moscow. It was paid for by NASA, a $220 million contract that gave the United States crucial hardware while keeping Russian engineers employed. 2 weeks later, on December 4th, Space Shuttle Endeavour launched carrying Unity, the first American-built node. On December 6th, astronauts used the shuttle's robotic arm to capture Zarya from orbit. They connected it to Unity in a delicate maneuver that had to be perfect. Any damage to the docking mechanisms could have ended the station before it truly began. When the two modules locked together, astronauts Jerry Ross and James Newman conducted 3 spacewalks to connect power cables, data lines, and life support systems between modules built on different continents using different measurement systems. On December 10, 1998, Mission Commander Robert Cabana and Russian cosmonaut Sergei Krikalev floated through the hatch into the connected modules, the first humans to enter what would become the ISS. But the infant station couldn't support life yet. It had no permanent power, no oxygen generation, no crew quarters. It would remain empty for nearly 2 years while more modules were added and systems brought online. What follows is a construction story unlike any other. Over the next 13 years, more than 40 launches from 5 space agencies delivered components. Russian Progress and Proton rockets, American space shuttles, European Ariane vehicles, Japanese H-2 rockets. Each carried pieces of a puzzle that could only be assembled in the vacuum of space. Modules arrived one at a time. Zvezda in 2000, Destiny in 2001, Quest, Harmony, Columbus, Kibo. Massive solar arrays unfurled like wings. Radiators spread to dissipate heat. Robotic arms reached out to grab new pieces and position them precisely. By 2011, when the final major American component was installed, the ISS stretched 109 meters from end to end, longer than a football field. It weighs approximately 420,000 kilograms. It contains 16 pressurized modules with a combined volume roughly equal to a 6-bedroom house. Solar arrays generate up to 120 kilowatts of power. Thermal radiators reject waste heat into space. Life support systems recycle air and water. Communication systems link to ground stations across multiple continents. This is not a machine built by one nation. Russian modules provide propulsion and docking ports. American modules house laboratories and life support. The European Columbus Laboratory conducts materials science. Japan's Kibo includes an external platform for exposing experiments to space. Canada provided the essential robotic systems. Italy built multi-purpose logistics modules. This orbital structure represents cooperation between nations that have been adversaries, partners forced together by economics and physics, creating something none could build alone. And all of it, every module, every solar panel, every system, is constantly on the verge of falling out of the sky. Orbital mechanics, the elegant truth of constant fall. The International Space Station orbits at an average altitude of approximately 400 kilometers. If you could drive your car straight up at highway speed, you'd reach that height in just over 2 hours. It's not far in the cosmic sense. The Moon, by comparison, orbits at 384,000 kilometers, nearly 1,000 times more distant. The ISS is so close to Earth that it still experiences atmospheric drag from the outermost wisps of our atmosphere. And this is where most explanations of spaceflight get it wrong. The ISS isn't above gravity. Earth's gravitational pull at 400 kilometers altitude is still about 90% as strong as it is on the surface. If you could somehow place the station on invisible stilts at that height, astronauts would feel nearly normal weight. The station isn't escaping gravity. It's surrendering to it completely. Here's what's actually happening. The ISS is traveling forward at 28,000 kilometers per hour, about 7.66 kilometers every second. At this tremendous speed, it falls toward Earth roughly 3 meters per second. But Earth's surface curves away beneath it by that same amount. For every meter the station drops, the planet curves away 1 meter. The result? Continuous freefall that never reaches the ground. It falls around the planet rather than into it. This is orbit. Not floating. Not anti-gravity. Just falling, forever, at precisely the right speed and altitude, so that the curve of the fall matches the curve of the planet. Every 90 minutes, the station completes 1 full lap around Earth. 16 orbits per day. That's 16 sunrises, 16 sunsets, days and nights compressed into frantic cycles that have nothing to do with human biology. The station's orbit is inclined at 51.6 degrees to the equator. This wasn't chosen arbitrarily. That angle allows launches from both American and Russian spaceports. It also carries the station over approximately 80% of Earth's inhabited surface, allowing observation of most human populations and geographic regions. But it means the station's path across the Earth shifts constantly, tracing a sine wave that covers different ground on each pass. Yet even this carefully maintained orbit is unstable. The ISS operates in what's called low Earth orbit, where traces of atmosphere still exist. At 400 kilometers, the atmosphere is incredibly thin, 1 billion times less dense than at sea level. But at 28,000 kilometers per hour, even that whisper of air creates drag. Oxygen molecules, nitrogen, stray atoms of helium. Each collision slows the station infinitesimally. Those tiny slowing forces compound. Every day, the ISS loses approximately 100 meters of altitude from atmospheric drag. That doesn't sound like much, but over weeks and months, it adds up. Without intervention, orbital decay would bring the station down in less than a year. Even operating normally, it would re-enter and burn up within 2 to 3 years if completely abandoned. This means the station must be regularly reboosted, pushed back up to its proper altitude. Russian Progress cargo spacecraft dock to the station, fire their thrusters to add velocity. The station's own Zvezda module can also perform reboosts. These burns happen every few months, nudging the station higher, compensating for the slow atmospheric bleeding of speed and altitude. The ISS is not sitting still up there. It's in constant motion, constant adjustment, constant controlled fall. Ground controllers track its position to within meters. They calculate future trajectories weeks in advance. When space debris is detected on a collision course, and with tens of thousands of trackable objects in orbit, this happens occasionally. The station can be maneuvered out of the way. Small debris, the size of paint flakes or metal fragments, are simply endured. The modules are shielded, but impacts happen regularly. Larger debris demands evasive action, careful thruster burns that change the orbit just enough to avoid catastrophe. Living aboard the ISS means living in a structure that is always moving, always falling, always adjusting. There is no stillness here. Even when astronauts sleep, the station hurtles through space at speeds that would cross the United States in less than 10 minutes. And everything inside falls with it, which creates the sensation we mistakenly call weightlessness. The astronauts aren't weightless. They're in free fall. Their weight exists, but it's canceled by their constant acceleration toward a planet they can never quite reach. This is the elegant lie of orbit. Motion, disguised as stillness, falling disguised as floating, and survival measured by staying just fast enough to never quite come home. Daily routines. Making the abnormal normal life aboard the ISS follows schedules so precise they would make a Swiss watchmaker proud. Every minute accounted for, every task planned, and all of it synchronized to a clock that has nothing to do with the sunrise or sunset outside the windows. The station operates on Coordinated Universal Time, UTC, also known as Greenwich Mean Time. This means morning begins at the same moment for astronauts above the Pacific, Africa, or anywhere else on their orbital path. Regardless of what the sun is doing outside, and remember, it rises every 90 minutes in orbit, crew wake-up is scheduled for 6 to 6:30 a.m. UTC. That's when alarm clock apps on their laptops gently rouse them from sleep sacks velcroed to the walls of their tiny crew quarters. The first task is simply becoming human again. In microgravity, sleep can be disorienting. Many astronauts report vivid dreams, likely because their inner ear, which normally helps orient the body, provides chaotic signals in freefall. Some sleep with arms floating in front of them, hands occasionally drifting up to brush their faces, startling them awake. Others secure their arms inside their sleeping bags to prevent this. After waking, the daily conference call begins around 7:30 a.m. Mission control on the ground, whether in Houston, Moscow, or other partner locations, briefs the crew on the day's tasks, overnight events, and any changes to the schedule. These calls happen multiple times each day. The station is never truly alone. Constant communication links it to Earth, though with a slight time delay that reminds everyone this conversation is happening across the void. Breakfast comes next. Food preparation in space is an art form of rehydration and careful eating. Most food is either freeze-dried, thermostabilized, heated to kill bacteria and sealed, or irradiated. Freeze-dried food requires adding hot water and waiting several minutes for it to rehydrate. Thermostabilized food can be eaten from the pouch or warmed in a small oven. Fresh fruit and vegetables arrive with cargo ships but must be consumed quickly before they spoil. Eating without gravity is a delicate process. Liquids cling to their containers through surface tension. Food floats away if not secured. Salt and pepper come as liquids because granules would disperse through the cabin and potentially clog air filters or drift into sensitive equipment. Crumbs are similarly forbidden, which is why bread is replaced by tortillas that hold together better. The station has a menu of more than 300 items. Not because astronauts are gourmets, but because variety helps maintain morale on missions lasting months. There's Russian borscht and American macaroni and cheese, Japanese curry, and European desserts. Special holiday meals include turkey and stuffing for supper. Thanksgiving, traditional foods for Russian holidays, and occasional surprises sent up on cargo ships. Astronauts can even request favorite foods to supplement the standard menu. After breakfast, the workday begins in earnest. Astronauts typically spend 6 to 8 hours on scheduled tasks. This might mean conducting scientific experiments, growing plants, studying combustion in microgravity, observing how materials behave without convection currents, or maintenance tasks, replacing air filters, checking life support systems, cleaning water recycling equipment, or preparation for upcoming events, reviewing procedures for a spacewalk, unpacking a newly arrived cargo vehicle, preparing equipment for an experiment. The ISS is a workplace, not a vacation. The $150 billion investment exists primarily for scientific research. Astronauts are highly trained technicians, following detailed procedures written by scientists on Earth. They photograph experimental results. They collect data. They describe observations. They adjust equipment and document anomalies. Most experiments are designed and monitored by researchers who will never leave Earth, with astronauts serving as their hands in space. Then there's exercise. 2 hours per day, mandatory, non-negotiable. This isn't optional fitness. It's medical necessity. In microgravity, muscles atrophy rapidly. Bones lose density at an alarming rate. Without exercise, astronauts would return to Earth so weakened they couldn't stand. So they run on a treadmill while strapped down with bungee cords. They use a resistance device that simulates weightlifting. They cycle on a stationary bike. The goal isn't fitness in the traditional sense. It's preventing catastrophic deterioration. Maintenance consumes another significant portion of each week. The ISS is a complex machine operating in a hostile environment. Systems fail, filters clog, equipment breaks. Astronauts must repair what they can, replacing components and troubleshooting problems. Some repairs require spacewalks, donning suits and going outside to fix external equipment. Others involve swapping modules inside the station, a task complicated by the fact that everything floats and nothing stays where you put it. Lunch happens around midday. Then more work, perhaps preparing for the next crew arrival, perhaps photographing Earth for science or outreach, perhaps installing new equipment just delivered. The station supports research across disciplines: biology, physics, material science, Earth observation, technology demonstration, human physiology. Each experiment has specific protocols, specific timing, specific data collection requirements. Dinner is a more social event. The crew, typically 6 or 7 people from multiple nations, gathers to eat together when schedules allow. They float around a table that exists more as tradition than necessity. They share food, tell stories, talk about home. These moments of normalcy matter. Psychological. Health is as important as physical health on long-duration missions. Isolation, confinement, and separation from family create stresses that can undermine crew cohesion. Evening includes communication time, phone calls home through internet-based phone systems, emails to family and friends, occasionally live video chats with loved ones. NASA schedules regular opportunities for crew to connect with Earth, understanding that maintaining those bonds helps astronauts endure the separation. Before sleep, there's hygiene. Showering is impossible. Water doesn't fall, and creating a pressurized water booth risks flooding the cabin with floating globules. Instead, astronauts use wet towels and rinseless shampoo. Toothbrushing happens carefully, with the paste swallowed afterward rather than spit out. Going to the bathroom requires using a toilet with a suction system that pulls waste away from the body. Urine is collected into a tank and processed into drinking water. Solid waste is stored in sealed containers and eventually loaded onto cargo ships for disposal, burned up during re-entry. Then, sleep. 8 hours allocated, though many astronauts report difficulty sleeping in microgravity. The sleeping compartments are phone booth-sized modules with sleeping bags attached to the walls. Some astronauts zip themselves in completely. Others leave their arms out. A few prefer sleeping in the larger laboratory modules. Finding more space somehow makes the experience more restful. White noise machines mask the constant hum of fans and equipment. Eye masks block the sun that rises outside every 90 minutes. And then the cycle begins again. Wake, conference, breakfast, work, exercise, maintenance, lunch, work, dinner, hygiene, sleep, day after day, week after week, month after month. The average ISS mission lasts 6 months. Some extend to a year for specific research purposes. During that time, the crew lives in an environment smaller than most houses, with people they didn't choose, doing work scheduled down to the minute, while their bodies slowly deteriorate and the world they know continues without them 400 kilometers below. They make it look routine. They smile for the camera. They conduct live broadcasts showing off the wonders of space. But underneath that carefully maintained normalcy is a profound psychological challenge. Making yourself believe that living in a falling metal tube surrounded by vacuum is somehow normal. That this is just another day at the office. That home is only a few months away. It's a testament to human adaptability that they succeed. Food and water. The chemistry of survival. When Space Shuttle Endeavour delivered the first crew to the ISS in November 2000, it brought food for the initial 4-month stay. Freeze-dried packets, thermostabilized pouches, energy bars, drink mixes. About 1.8 kilograms of food per person per day, carefully chosen for nutrition, variety, and shelf stability. At that rate, food for a 6-person crew for a year would weigh nearly 4,000 kilograms. Launching that much mass costs millions of dollars. But it's not the food that's the real challenge. It's the water. A human needs approximately 2 to 3 liters of water per day for drinking. Add water for food preparation, oral hygiene, and hand washing, and the requirement increases. The ISS life support systems target about 3.5 liters per person per day. For a crew of 6 over a year, that's over 7,500 liters. At approximately $10,000 per kilogram to launch into orbit, and water weighs 1 kilogram per liter, supplying water alone would cost $75 million per year. This isn't sustainable. For the ISS to function long-term, and for future missions to the Moon or Mars to be feasible, water recycling isn't optional. It's essential. Enter the Environmental Control and Life Support System, ECLSS, specifically its water recovery system. This complex collection of hardware captures every drop of moisture aboard the station. Humidity from crew breathing and perspiration is pulled from the air by dehumidifiers and condensed into liquid. Urine is collected in the waste and hygiene compartment and pre-treated with chemicals to prevent bacterial growth and mineral precipitation. Even the water vapor produced by the oxygen generation system gets recovered. All this wastewater flows to the water processor assembly. The urine first passes through the urine processor assembly, where vacuum distillation separates water from dissolved solids, producing a urine distillate and concentrated brine. Early systems could only recover about 75% of the water from urine. The rest remained locked in that brine, a salty sludge that was stored and eventually discarded. But in 2021, NASA added the brine processor assembly, a technological upgrade that changed everything. The BPA takes that concentrated brine and passes it through a series of membranes while blowing warm, dry air across it. This causes the remaining water to evaporate. That humid air is then captured by the station's existing dehumidifiers, condensed, and added back into the water processing stream. With this system operating, the ISS achieved a milestone in 2023, 98% water recovery. That means launching with 100 liters of water, losing only 2 liters to waste, and recycling the other 98 liters indefinitely. The 2% loss is replaced with water delivered by cargo ships, but the reduction in required resupply is dramatic. Think about what this means. When an astronaut drinks a pouch of water, that water contains hydrogen and oxygen atoms that have been inside other crew members, breathed out as vapor, excreted as urine, sweated through skin. The water processor assembly uses filtration, chemical treatment, and a catalytic reactor to break down trace contaminants. Sensors verify water purity before it's released for crew consumption. If it doesn't meet standards, it's reprocessed until it does. NASA is fond of saying, today's coffee is tomorrow's coffee. The saying is technically accurate. The water molecules don't change. They're captured, purified, and returned to use. Chemically, the water emerging from the WPA is cleaner than most tap water on Earth. But psychologically, drinking recycled urine requires a mental adjustment that not everyone finds easy. Yet this is the reality of long-duration spaceflight. Water is too heavy and expensive to launch in sufficient quantities. It must be recycled with extreme efficiency. The 98% recovery rate on the ISS is impressive, but Mars missions will likely require 99% or higher because resupply from Earth would take months and cost exponentially more. The ECLSS doesn't just recycle water. It also generates oxygen through electrolysis, running electrical current through water to split it into hydrogen and oxygen. The oxygen goes into the cabin atmosphere. The hydrogen is usually vented overboard, though some is combined with carbon dioxide in the Sabatier reactor to produce water and methane. This closes part of the loop, converting waste CO2 back into usable water, though the Sabatier system has experienced failures and isn't always operational. Carbon dioxide removal happens through multiple systems. Scrubbers pull CO2 from the air. Some systems vent it overboard. Others attempt to process it. Managing the cabin atmosphere is a constant balancing act. Oxygen concentration, CO2 levels, humidity, temperature, pressure. All must be maintained within narrow ranges to keep the crew healthy and equipment functioning. The station's atmosphere is similar to Earth's at sea level. Approximately 21% oxygen, 78% nitrogen, with trace gases making up the remainder. Pressure is maintained at around 101 kilopascals, 14.7 psi. If pressure drops, alarms sound. If it drops too far, the crew would have minutes to don emergency oxygen masks before hypoxia set in. Food preparation requires water from the recycling system. Freeze-dried scrambled eggs? Add hot water and wait 5 minutes. Macaroni and cheese? Rehydrate with warm water and knead the pouch to mix. Coffee and tea? Hot water infused with drink crystals. Almost every meal involves rehydration, which means the entire food supply depends on the water recovery systems functioning continuously. When those systems fail, and they do fail, the crew can survive for some time on backup water tanks filled from cargo ships. But a prolonged failure would force difficult decisions. Reduce crew size to conserve water. Launch emergency resupply at enormous cost, or even abandon the station. Water is life. Without it, the ISS becomes a tomb within weeks. The psychological adaptation required to trust this system is profound. You drink water, knowing its origins. You prepare food with water that has an intimate history. You trust that filtration, chemistry, and engineering have transformed waste into sustenance. And every time you take a sip, you participate in a cycle of renewal that turns endings into beginnings, that extracts value from discards, that makes survival possible in an environment designed to kill you. That trust in technology, in systems, in the invisible processes purifying what you consume, is as essential as the water itself. A science laboratory, unlike any other. The ISS contains more than living quarters and life support systems. Embedded within its modules are laboratories equipped with racks of experimental equipment, instruments sensitive to vibration and temperature, facilities for biological research, materials science, physics, Earth observation, and technology demonstration. It's a laboratory that exists in an environment impossible to recreate on Earth: long-term microgravity. Over the station's operational life, more than 4,000 investigations have been conducted. Research from universities, corporations, space agencies, and government institutions. Experiments studying protein crystal growth, which is enhanced in microgravity, and allows for more detailed analysis of molecular structures that inform drug development. Research on combustion behavior, because fire burns differently without convection currents. Flames form spheres rather than teardrop shapes, burning cooler and slower, which has implications for engine design and fire safety. Materials scientists use the ISS to study how metals, alloys, and crystals form without the gravitational settling that affects Earth-based manufacturing. In microgravity, temperature differences don't create convection. Heavier materials don't sink. This allows the creation of advanced alloys and structures with unique properties that could lead to stronger, lighter materials for aerospace applications, or new superconductors that only form properly in the absence of gravity. Biological experiments range from the microscopic to the complex. Cells behave differently in microgravity. Some grow faster, others change shape. Certain cellular processes activate or deactivate. Researchers study these changes to understand fundamental biology and to develop tissue chips that model human organs in space. These chips could accelerate drug testing by simulating organ function more accurately than cell cultures on Earth. Plant growth in space is both research and practical necessity. Future long-duration missions will need to grow food, but plants evolved to use gravity for directional cues. Roots grow down, shoots grow up. In microgravity, plants must orient using light, moisture, and chemical gradients. Experiments aboard the ISS have successfully grown lettuce, radishes, peppers, and other crops in specialized plant chambers. Astronauts have eaten some of these fresh vegetables, a welcome change from freeze-dried and thermostabilized meals, while scientists study how microgravity affects growth rates, nutrient content, and genetic expression. Earth observation is another major research area. From 400 kilometers up, astronauts photograph hurricanes, volcanic eruptions, city growth, deforestation, ocean phenomena, and atmospheric events. The station's cameras capture images used by climate scientists, disaster responders, urban planners, and environmental researchers. The view from the ISS provides a perspective that satellites can't match. Human observers who can notice unexpected events, frame shots creatively, and document rapidly changing situations. Physics experiments include studying Bose-Einstein condensates, exotic states of matter that only form at temperatures near absolute zero. The ISS houses the Cold Atom Laboratory, which creates these condensates in orbit and studies their behavior. Without gravitational interference, the condensates last longer and can be observed in greater detail. This research has implications for quantum physics, atomic clocks, and potentially future sensing technologies. The station serves as a test bed for technologies destined for deeper space. Water recycling systems, radiation shielding materials, closed-loop life support, autonomous robotics, advanced materials. If a technology might be needed for a lunar base or Mars mission, it's often tested aboard the ISS first, where failures can be repaired and lessons learned before lives depend on perfect operation, billions of kilometers from help. Human research is perhaps the most critical. Every crew member is a research subject, participating in studies of bone density loss, muscle atrophy, cardiovascular changes, vision impairment, immune system function, sleep patterns, psychological health, and more. This research isn't academic. It directly informs how future missions will be designed, how long humans can safely remain in space, and what countermeasures might allow us to explore beyond Earth's immediate neighborhood. The very structure of the station enables this research. Microgravity isn't a location, but a condition: freefall. The ISS orbits fast enough that its freefall matches Earth's curvature, creating continuous weightlessness. This allows experiments to run not for seconds or minutes, as they would in a drop tower or parabolic flight, but for months or years. Long-duration exposure reveals effects that short-term experiments never could. The science isn't glamorous. It's often tedious. Astronauts follow detailed procedures, photographing results, collecting samples, transferring data. They calibrate instruments, replace components, troubleshoot equipment failures. They're technicians as much as explorers. But the knowledge gained about materials, biology, physics, human physiology, Earth systems, justifies the extraordinary cost of maintaining a laboratory that circles the planet at 28,000 kilometers per hour. Every experiment teaches us something about how matter and life behave when released from gravity's constant pull. Some lessons are practical, leading to new materials or medicines. others are fundamental, reshaping our understanding of physics or biology. All of them contribute to a larger question: can humanity survive beyond Earth? And if so, how? The ISS doesn't answer that question definitively, but it provides data points, proof of concept, and hard-won experience. It shows us what works and what fails, what humans can endure and what they cannot, what technologies are robust enough for deep space and which need further development. In that sense, the ISS is less a destination than a stepping stone, a place to learn before taking the leap into environments even more hostile and even farther from home. How spaceflight changes the human body. Here's a truth that NASA doesn't often lead with. Going to space slowly destroys your body. Not immediately, not dramatically, but persistently, measurably, and sometimes permanently. Bone loss begins within days. In microgravity, bones don't bear weight. The mechanical stress that normally triggers bone formation, the constant loading from standing, walking, running, vanishes. The body interprets this as a signal that the bones are stronger than necessary and begins breaking them down to reclaim calcium and other minerals. Astronauts lose approximately 1 to 1.5% of bone mass per month, primarily in weight-bearing bones like the hips, spine, and legs. That might not sound severe, but over a 6-month mission, that's 9% bone loss, comparable to decades of osteoporosis on Earth compressed into half a year. Longer missions mean greater loss. By the time astronauts return to Earth, their bones are significantly weaker, more brittle, more prone to fracture. Exercise helps slow the loss, but doesn't prevent it. Intensive treadmill running, resistance training, and careful nutritional management reduce the rate of deterioration, but can't eliminate it entirely. Muscle atrophy follows a similar pattern. Without gravity to resist, muscles don't work as hard. The body begins breaking down muscle tissue, especially in the legs and core. Studies show that astronauts can lose up to 20% of muscle mass in the first 5 to 11 days of spaceflight. Again, exercise helps, but 2 hours daily on a treadmill and resistance device can't fully replicate the constant muscular engagement required by Earth's gravity. Bone recovery after returning to Earth is slow and incomplete. Research suggests it takes roughly 3 years to regain bone density lost during a 6-month mission, and some aspects of bone architecture may never fully recover. This raises profound questions about the feasibility of longer missions to Mars or beyond, where astronauts might spend years in low-gravity environments. Are we building spacecraft to destinations our bodies simply cannot reach? Vision changes were first noticed when astronauts began spending months aboard the ISS, and they revealed something NASA hadn't anticipated. Many crew members reported trouble focusing on nearby objects, a condition similar to farsightedness. But medical examinations revealed something far more concerning. The optic nerve swelled, the back of the eyeball flattened, and in some cases, astronauts experienced structural changes in their eyes that persisted long after returning to Earth. Permanent alterations from what was supposed to be temporary exposure to microgravity. This condition, now called space-associated neuroocular syndrome, SANS, appears to be related to increased pressure on the brain from the fluid shift upward. In microgravity, cerebrospinal fluid doesn't drain downward as it does on Earth, which suggests that pressure builds around the brain and optic nerves, causing swelling and structural changes. Some astronauts have experienced permanent vision impairment from these effects, a sobering discovery that emerged only after humans began spending extended time in space. It's a reminder that despite decades of spaceflight, we're still discovering fundamental ways that leaving Earth changes us. The fluid shift affects more than vision. On Earth, gravity pulls blood toward the legs. The cardiovascular system is designed to pump blood upward against that pull. In microgravity, blood redistributes toward the chest and head. Astronauts develop puffy faces and congested sinuses that don't clear until they return to Earth. The heart, no longer working against gravity, begins to atrophy slightly. Blood volume decreases because the body senses that less is needed. When astronauts return to Earth, standing up becomes difficult. Their cardiovascular systems struggle to pump blood against gravity again after months of disuse. The immune system also changes in space. The stress of spaceflight, combined with isolation, radiation exposure, and disrupted sleep patterns, seems to suppress immune function. Dormant viruses in astronauts' bodies, like herpes viruses that lie dormant in most humans, can reactivate. Wound healing slows. The risk of infection increases. The exact mechanisms aren't fully understood, but the pattern is clear. The immune system operates less effectively in space. Radiation exposure is an ongoing concern. The ISS orbits within Earth's magnetosphere, which provides significant shielding from cosmic rays and solar radiation. But even here, radiation exposure is about 10 times higher than on Earth's surface. Astronauts accumulate dosage over time, increasing their lifetime cancer risk. For missions beyond Earth orbit, to the Moon or Mars, radiation exposure would be far worse. The ISS helps researchers study radiation effects and test shielding technologies, but perfect protection remains elusive. Psychological effects are harder to quantify, but no less real. Isolation from family, confinement in a small space with no escape, constant work under public scrutiny, the knowledge that any mistake could be fatal. All of this creates stress. Most astronauts handle it remarkably well, supported by careful psychological screening, regular communication with loved ones, and counseling when needed. But psychological resilience has limits, and understanding those limits is critical for planning longer missions to more isolated destinations. Sleep disruption is nearly universal. The sunrise every 90 minutes interferes with circadian rhythms. Some astronauts struggle with insomnia. Others sleep fitfully, waking frequently. Sleep deprivation affects cognitive function, mood, and performance. The station's crew quarters have been designed to minimize light and sound, and astronauts use sleep aids when necessary. But the fundamental problem remains. Human biology evolved for 24-hour day-night cycles, and the ISS provides nothing of the kind. And here's the uncomfortable truth that underlies all of this. We don't fully understand the long-term consequences. The longest single spaceflight was 437 days by Russian cosmonaut Valery Polyakov aboard Mir. Some cosmonauts have accumulated over 800 days across multiple flights. These are data points, not comprehensive answers. What happens after 2 years? 5 years? 10? If humans journey to Mars, the trip alone will take 6 to 9 months each way. The surface stay would likely be 1 to 2 years to wait for Earth and Mars to align favorably for the return trip. That's nearly 3 years in reduced gravity with no possibility of early return. We have no data on how the human body responds to such duration. Based on what we know, we can assume bone loss would be severe. Muscles would atrophy significantly. Vision changes might be profound. And cardiovascular reconditioning on return might take years. But we don't know for certain. The ISS serves as our laboratory for understanding these effects. Every astronaut who spends 6 months aboard contributes data. Medical tests before, during, and after their missions track changes. Countermeasure effectiveness is evaluated. New exercise protocols are tested. Better nutrition strategies are tried. Slowly, incrementally, we're learning how to keep humans healthy in space for longer durations. But the shadow of uncertainty remains. We know space changes us. We know those changes can be profound and sometimes permanent. What we don't fully know is whether those changes will ultimately prevent us from becoming a spacefaring species, or whether human ingenuity can develop countermeasures effective enough to overcome biology's limitations. The astronauts aboard the ISS right now are participants in a grand experiment. Their bodies are test cases. They're sacrifices, because bone loss and vision changes are sacrifices, are paid in service of knowledge that might one day allow humans to venture farther from Earth. They smile for the cameras. They exercise diligently. They follow medical protocols. And slowly, cell by cell, their bodies change in ways that won't fully reverse until years after they come home, if ever. Spacewalks. Operating in the void. Since assembly of the ISS began, astronauts and cosmonauts have performed more than 270 spacewalks, totaling over 1,700 hours. Outside the station, these EVAs have installed new modules, upgraded equipment, repaired failing systems, and maintained the station's exterior. Without spacewalks, the ISS could not have been built or maintained. Yet here's what makes spacewalks remarkable. The records keep falling. For over 23 years, NASA astronauts James Voss and Susan Helms held the record for the longest single spacewalk, 8 hours and 56 minutes, set on March 11, 2001, during ISS construction. It seemed an almost insurmountable achievement, pushing human endurance in hostile conditions to its limits. Then, in December 2024, Chinese astronauts Kai Shuzhe and Song Lingdong shattered that record aboard the Tiangong space station. They spent 9 hours and 6 minutes outside their spacecraft, a duration that pushed even their Phaeton spacesuits beyond their designed 8-hour operational limit. Ground controllers had to carefully monitor each suit's life support consumables as the spacewalkers edged into their safety margins. The tasks apparently took far longer than planned, suggesting something went wrong or proved more complex than expected. Yet they persevered, setting a new benchmark that demonstrates how far human spacewalking capabilities have evolved since that first terrifying 12-minute venture by Alexei Leonov in 1965. Preparing for any spacewalk takes days. The spacesuit, technically called an Extravehicular Mobility Unit or EMU for NASA missions, is essentially a personal spacecraft. It provides oxygen, removes carbon dioxide, maintains pressure, controls temperature, shields against radiation, and protects from micrometeoroids that streak through space at thousands of kilometers per hour. The suit includes 14 layers of insulation and protective materials, a hard upper torso shell to protect vital organs, and a complex life support backpack. But the suit itself creates problems, specifically pressure problems. Inside the ISS, atmospheric pressure is about 101 kilopascals, 14.7 psi, similar to Earth's sea level. But the EMU operates at only 29.6 kilopascals, 4.3 psi. This lower pressure is necessary because a suit pressurized to full Earth atmosphere would be too stiff for astronauts to bend their joints. Even at reduced pressure, the gloves are so rigid that gripping tools require significant hand strength, and many astronauts return from EVAs with bruised, sore hands and fingernails. Moving from 101 kPa to 29.6 kPa creates a risk. Decompression sickness, the same bends that affects divers who surface too quickly. Nitrogen dissolved in the blood can form bubbles if pressure drops too rapidly. Those bubbles can cause joint pain, tissue damage, even strokes or death in severe cases. To prevent this, astronauts pre-breathe pure oxygen for several hours before a spacewalk. During this time, they breathe 100% oxygen, while the station's atmospheric pressure is sometimes temporarily lowered to help nitrogen wash out of their tissues. This process typically lasts about 4 hours. 4 hours of sitting in the airlock, doing nothing but breathing, preparing their bodies for the transition to vacuum. Once the pre-breathe is complete, the airlock depressurizes. The astronauts, now fully suited and breathing from their EMU's oxygen tanks, wait as air is pumped out and into storage tanks. When pressure reaches zero, the outer hatch opens. Stepping outside is unlike anything experienced on Earth. The ISS structure stretches in all directions. Far below, 400 kilometers below, Earth fills the view, massive and brilliant. The sun, unfiltered by atmosphere, burns with searing intensity. Temperature swings are extreme. In direct sunlight, surfaces can reach 120 degrees Celsius. In shadow, they plunge to 100 degrees Celsius. Or colder. The EMU's thermal control system must manage these swings, circulating cooling water through tubes in the undergarment when in sun, providing insulation when in shadow. Silence. There's no air to carry sound. Vibrations can be felt through tools or the station structure, but there's no wind, no rustling, no ambient noise. Astronauts communicate through radio. Their voices the only sound in an environment utterly without it. Movement is deliberate and slow. Astronauts are tethered at all times. Safety tethers connect them to the station structure, preventing them from drifting away. A second backup tether provides redundancy. They clip and unclip tethers as they move, always maintaining at least one attachment point. Tools are also tethered. Everything is secured because anything dropped in space doesn't fall. It enters its own orbit, potentially at high relative velocity, becoming dangerous debris. Tasks that would take minutes on Earth require hours. Installing a new equipment rack, replacing a failed component, running new cables. Each action is methodical. The rigid suit fights every motion. Gloves make fine manipulation nearly impossible. Tools must be specially designed for use in pressurized gloves. Astronauts rehearse procedures underwater in NASA's Neutral Buoyancy Laboratory, where they practice in near-weightless conditions for hours, preparing for the actual spacewalk. Fatigue sets in. The physical effort of working against the suit's stiffness is exhausting. Hands cramp, shoulders ache. The mind must stay focused despite fatigue because mistakes outside can be fatal. Astronauts drink water through tubes in their helmets, but eating is impossible during an EVA. They rely on pre-mission nutrition and sheer endurance. Emergencies are rare, but catastrophic when they occur. In 2013, Italian astronaut Luca Parmitano experienced a water leak in his helmet during an EVA. Water began filling his helmet, covering his face, blocking his nose and mouth. In microgravity, the water didn't drain. It spread as a floating blob, threatening to drown him. He and his partner aborted the EVA immediately, returning to the airlock. Parmitano had difficulty seeing and breathing during the rush to safety. The leak, caused by a contaminated filter in the suit's cooling system, could have killed him. NASA suspended spacewalks for months while engineers investigated and redesigned the system. That incident reminds us that spacewalks are never routine. Every EVA carries risk. Suits can fail. Tethers can snag. Micrometeoroid impacts, though rare, could puncture a suit. Astronauts train for emergencies, but some scenarios have no good solution. If a suit catastrophically fails far from the airlock, the astronaut would have perhaps 15 seconds of useful consciousness before hypoxia and embolism set in. Rescue might not be possible in that time. The simplified aid for EVA rescue, SAFER, provides a last resort option if an astronaut somehow becomes untethered. This small jetpack uses nitrogen gas thrusters to allow self-rescue, providing limited maneuvering capability to return to the station. It's tested regularly, but has never been needed in an actual emergency. A testament to the effectiveness of tethers and safety procedures, though one wonders how long that perfect record can last as spacewalks continue. For cumulative spacewalking experience, Russian cosmonaut Anatoly Solovyev holds an extraordinary record. 82 hours and 22 minutes across 16 spacewalks, performed during 4 different Mir missions between July 1990 and January 1998. That's more than 3 full days spent working in the vacuum of space. American astronaut Michael Lopez Alegria completed 10 spacewalks totaling 67 hours and 40 minutes. Among European astronauts, Thomas Pesquet leads with 6 EVAs, totaling nearly 40 hours. These veterans represent the accumulated experience that makes modern spacewalks safer and more efficient than ever. When the EVA is complete, astronauts return to the airlock, close the outer hatch, and wait as air is slowly bled back in from storage tanks. Repressurization takes time to prevent damaging the suits or the airlock. Once pressure equalizes with the interior, the inner hatch opens and the astronauts float back inside. But they're not done. The suits must be inspected, cleaned, and recharged. Oxygen tanks refilled, water reservoirs replenished, batteries recharged, carbon dioxide scrubbers replaced. Any damage must be documented and, if possible, repaired. Each suit represents a multi-million-dollar investment and weeks of refurbishment between uses. Astronauts often describe spacewalks in terms that sound contradictory: terrifying and peaceful, exhausting and exhilarating, routine and utterly alien. To work outside, tethered to a structure falling around the Earth at 28,000 kilometers per hour, surrounded by vacuum and radiation, with only a carefully engineered suit between you and death, that requires a particular kind of courage. Or perhaps it requires compartmentalization so complete that the terror is simply filed away, acknowledged, but not allowed to interfere with the work. Either way, spacewalks are humanity's most direct confrontation with the hostility of space. No module walls, no atmosphere, just you, your suit, and an environment that wants you dead. And yet, astronauts do this voluntarily, repeatedly, for hours at a time. Because sometimes, the only way to fix something in space is to go outside and touch it with human hands. And as long as humans live and work in orbit, that will remain true. Life support systems. The fragile balance. The ISS is not self-sustaining. It cannot be. Every system aboard the station depends on resupply from Earth. Spare parts, filters, consumables, replacement hardware. But within those constraints, the Environmental Control and Life Support System, ECLSS, keeps the crew alive with remarkable efficiency. The system manages everything that makes the station habitable. Oxygen generation, carbon dioxide removal, atmospheric pressure regulation, temperature control, humidity management, water recovery, air filtration. Each subsystem must function continuously. Failures can be tolerated for a short time using backup systems, but prolonged failures would force evacuation. Oxygen comes from 2 primary sources. The oxygen generation system uses electrolysis to split water into hydrogen and oxygen. Electrical current passes through water, separating the molecules. The oxygen is released into the cabin atmosphere. The hydrogen is mostly vented overboard, though some is used in the Sabatier reactor when it's operational. This system can produce enough oxygen for the entire crew, though it requires a steady supply of water. Another reason water recycling is critical. Russian electron oxygen generators provide backup. These also use electrolysis, but with different hardware and operation. Having dual systems from different manufacturers provides redundancy. If one fails, the other can sustain the crew while repairs are made or spare parts are delivered. Oxygen canisters provide a third source. These solid fuel oxygen generators, SFOGs, are chemical candles that produce oxygen when ignited. They're emergency backups, used when primary systems fail or during periods of increased crew size when generation can't keep pace with consumption. Each candle burns for a specific duration, releasing oxygen steadily. They can't be extinguished once lit. They burn until the chemicals are exhausted. Carbon dioxide removal is equally critical. Humans exhale CO2 with every breath. In a closed environment, it accumulates rapidly. At low concentrations, CO2 causes headaches and fatigue. At higher levels, it impairs judgment and can be fatal. The station targets CO2 levels around 0.4% to 0.7% of atmospheric composition, compared to Earth's roughly 0.04%. Even at these elevated levels, long-term exposure may have health effects, but the alternative, heavier, more power-hungry CO2 removal systems, isn't practical with current technology. The Carbon Dioxide Removal Assembly, CDRA, uses a regenerable system with zeolite beds that adsorb CO2. Air is passed through the beds, which capture the CO2. When a bed becomes saturated, it's exposed to vacuum, releasing the captured CO2 into space. The bed is then ready to be used again. Two beds work in alternation. While one adsorbs, the other regenerates. Russian Vozduk systems provide similar functionality using different technology. Again, redundancy. The station can lose multiple CO2 removal systems and still maintain safe atmosphere using the remaining units, though at reduced crew capacity. Temperature control is more complex than it might seem. Heat in space doesn't radiate away quickly because there's no air to carry it. Heat must be actively rejected using radiators. The ISS has large thermal radiators that glow with infrared radiation, dumping waste heat into space. Fluids circulate through the station, collecting heat from equipment and crew, then flowing through the radiators to shed that heat. If the radiators fail or are damaged, temperature inside the station rises. Equipment overheats. The crew becomes uncomfortable and then endangered. Redundant cooling loops provide backup, but the thermal control system is one of the most critical and vulnerable systems aboard the station. Air circulation is constant. Fans move air throughout the modules, preventing pockets of stagnant CO2 from forming around crew members. On Earth, warm air rises and cool air sinks, creating natural convection. In microgravity, there's no convection. Without forced air circulation, an astronaut could create a bubble of exhaled CO2 around their head and slowly suffocate in their own breath while surrounded by fresh air just inches away. Atmospheric pressure is maintained by adding or removing gas as needed. Leaks are inevitable in a structure as large and complex as the ISS. Modules are sealed, but tiny gaps exist at hatches, around windows, through penetrations for cables and plumbing. The station leaks a small amount of air constantly. Sensors monitor pressure and trigger alarms if it drops too quickly. Crew can seal individual modules if a larger leak is detected, isolating the damaged section, while the rest of the station remains pressurized. Water recovery, as discussed earlier, achieves 98% efficiency through the water processor assembly and brine processor assembly. This system is so critical that losing it would shorten the station's operational life to the duration of backup water supplies. Weeks, perhaps months, depending on crew size and resupply schedules. Air filtration removes particulates, microbes, and trace contaminants. HEPA filters capture dust and particles. Charcoal filters absorb organic compounds and odors. These filters must be replaced regularly. Dirty filters reduce air quality and system efficiency. Fresh filters are delivered with cargo ships, a mundane but essential supply. The ECLSS is monitored continuously. Sensors throughout the station track oxygen levels, CO2 concentration, temperature, humidity, pressure, and dozens of other parameters. Ground controllers in Houston and Moscow watch these telemetry feeds 24 hours a day. Any anomaly triggers investigation. Small deviations are normal. Large or rapid changes demand immediate action. Crew members are trained to respond to life support failures. If CO2 levels spike, they know which backup systems to activate. If pressure drops, they know where to look for leaks. If temperature climbs, they know how to troubleshoot the thermal control system. But some failures can't be fixed quickly. If multiple systems fail simultaneously, a highly unlikely but possible scenario, the crew might have only hours to evacuate to the docked Soyuz or Crew Dragon spacecraft and abandon the station. The sobering reality is this: the ECLSS keeps the crew alive, but it does so with limited margins. There are backups, redundancies, and workarounds. But the station operates in an environment where failure is always one malfunction away. Engineers design with this in mind, building in tolerances, planning for contingencies, testing extensively before hardware launches. And yet, unexpected things happen. Filters clog sooner than predicted. Hardware ages differently in space than in ground testing. Micrometeoroid impacts damage components. Software glitches cause system shutdowns. The ISS has experienced all of these and more, and through quick thinking, clever engineering, and sometimes sheer improvisation, the crew and ground teams have kept the systems running. But there's no guarantee that luck holds forever. One day, a critical system might fail in a way that can't be quickly repaired. Spare parts might not be available. A resupply launch might be delayed by weather or technical issues. And in that window of vulnerability, the station's fate and the crew's survival would hinge on ingenuity, courage, and perhaps a bit of fortune. For now, the ECLSS hums quietly in the background. Air circulates. Oxygen flows. Carbon dioxide is scrubbed. Water is recycled. Temperature is maintained. And the crew breathes, drinks, and lives, trusting in systems they can't see and engineers they'll never meet. It's a fragile balance, but it's held for over 2 decades. And with continued vigilance, it may hold for years to come. Connection to Earth, the lifeline. That cannot break, the ISS is never truly alone. Every moment of every day, it remains connected to Earth through invisible threads of radio waves, data streams, and coordinated logistics. This connection is not optional. It is essential. Communication happens through the Tracking and Data Relay Satellite System, TDRSS, a network of satellites in geostationary orbit that relay signals between the ISS and ground stations. When the station passes over NASA ground stations in New Mexico, these stations also communicate directly. Russian ground stations provide additional coverage. Between these systems, the ISS maintains near constant contact with satellites, Earth. Voice communication, video feeds, email, telemetry data, experiment results, medical information, all flow continuously between station and ground. Mission control centers in Houston and Moscow monitor every system, ready to advise crew on procedures, troubleshoot problems, or coordinate responses to emergencies. The crew conducts daily planning conferences with ground controllers, reviewing schedules, discussing anomalies, and receiving updates on upcoming events. But communication is more than operational. It's psychological. Crew members speak with family through private phone lines. They send emails. They video chat. These connections to home matter immensely. Isolation is one of the hardest aspects of long-duration spaceflight. Maintaining family bonds, staying connected to friends, even participating in children's birthdays or school events through video. These aren't luxuries. They're necessities that keep astronauts mentally healthy. Resupply missions are the physical manifestation of Earth's support. The ISS cannot produce food. It cannot manufacture spare parts. It cannot generate repair materials from nothing. Everything must be launched from Earth. Cargo ships arrive every few months. Russian Progress spacecraft, SpaceX Dragon capsules, Northrop Grumman Cygnus vehicles, Europe's automated transfer vehicle, flew until 2014. Japan's H-2 transfer vehicle operated until 2020. Each cargo ship brings tons of supplies: food, water, oxygen, clothing, scientific equipment, spare parts, personal items for crew, and occasionally, fresh fruit and vegetables that must be consumed quickly. These launches are choreographed years in advance. Manifests are planned. Cargo is packed with precision. Weight and volume are carefully calculated. Critical items are prioritized. Backup supplies are staged in case a launch fails. And launches do fail. Rockets explode. Ships are lost. When a Progress spacecraft failed in 2015, the station lost months of supplies. Fortunately, other cargo ships were scheduled and could partially compensate. When a SpaceX Dragon exploded during a ground test in 2016, contingency plans shifted supplies to other vehicles. The ISS has enough backup capability that losing one resupply mission is manageable. Losing multiple missions in sequence would create serious shortages. Crew rotation depends on human-rated spacecraft. Currently, Russian Soyuz capsules and SpaceX Crew Dragon vehicles ferry astronauts to and from the station. At least one spacecraft must always be docked as a lifeboat in case of emergency evacuation. When a new crew launches, the departing crew uses an older vehicle to return home, ensuring a fresh lifeboat is always available. These crew rotation launches are timed carefully. Overlapping crews allow knowledge transfer. Experienced astronauts brief their replacements on station quirks, equipment oddities, and lessons learned. This continuity is critical. The station is complex, and no amount of ground training fully prepares you for actually living there. Institutional knowledge passed from crew to crew prevents repeated mistakes and maintains operational efficiency. Medical support relies entirely on Earth's expertise. The station has a small medical kit, some diagnostic equipment, and crew members with medical training. But for anything beyond minor injuries or illnesses, the crew depends on ground-based physicians who provide remote consultation. Telemedicine has been refined aboard the ISS. Doctors on Earth guide crew through examinations, review ultrasound images transmitted from space, prescribe treatments, and monitor recovery. If a serious medical emergency occurs, a stroke, heart attack, severe injury, the crew might have to return to Earth immediately. Emergency evacuations are possible. The docked Soyuz or Crew Dragon can undock and land within hours. But depending on where the station is in its orbit, landing sites might not be accessible. Weather might delay recovery, or medical facilities might be far from the touchdown point. For life-threatening emergencies in space, time is the enemy, and Earth is never as close as you'd like. Scientific collaboration requires constant data flow. Researchers on Earth design experiments, upload procedures to the station, and receive results back for analysis. This two-way exchange happens daily. Images, sensor data, biological samples preserved for return, video of experimental results. The ISS isn't an isolated laboratory. It's a node in a global research network with scientists across continents contributing to and analyzing data from orbit. Social media and public outreach also tie the station to Earth. Astronauts post photos, answer questions, conduct live interviews with schools and media. These activities serve dual purposes. They maintain public interest in space exploration, justifying continued investment, and they help astronauts feel connected to the broader world beyond their 6 crewmates. The station's existence depends on international cooperation that transcends politics. The ISS is managed by 5 space agencies: NASA, United States; Roscosmos, Russia; ESA, European Space Agency; JAXA, Japan; and CSA, Canada. These agencies contribute hardware, expertise, and funding. Despite geopolitical tensions, including sanctions, conflicts, and diplomatic disputes, the ISS partnership has remained functional because it serves everyone's interests. But that cooperation is fragile. When Russia invaded Ukraine in 2022, there were concerns that Roscosmos might withdraw from the partnership. potentially stranding crew or disrupting station operations. So far, cooperation has continued, but the incident revealed how vulnerable the ISS is to political shifts. The station's future depends not just on engineering and budgets, but on diplomacy and mutual interest. NASA has announced that the ISS will operate until at least 2030, with possible extension to 2032 after shut. That, the station will be deliberately deorbited, guided to burn up over the Pacific Ocean. This decision isn't made lightly. The ISS has been humanity's home in orbit for over 2 decades. But aging hardware, increasing maintenance costs, and the desire to redirect resources toward lunar and Mars exploration have led to this conclusion. Private space stations are planned to replace the ISS. Axiom Space is developing commercial modules that will initially attach to the ISS, then separate to form an independent station. Other companies, including Blue Origin and Northrop Grumman, have proposed their own stations. NASA intends to transition from owning and operating a station to becoming a customer, purchasing services from commercial providers. This approach, it's hoped, will reduce costs while maintaining a human presence in low Earth orbit. But until those commercial stations are operational, the ISS remains humanity's only continuous outpost beyond Earth, and it remains utterly dependent on the planet below for survival. Every calorie of food, every liter of water not recycled, every replacement part, every bite of instruction, every word of encouragement, all come from Earth. The crew lives 400 kilometers up, moving at 28,000 kilometers per hour, but their lifeline stretches down to the planet they're orbiting. If that lifeline were cut, if resupply stopped, if communication failed, if cooperation collapsed, the station would become a tomb. So far, the lifeline holds. But its strength depends on factors beyond engineering: political will, economic priorities, international relations, and the continued belief that this extraordinary orbital laboratory is worth sustaining. For now, Earth supports the ISS. The ISS, in turn, provides knowledge, inspiration, and perhaps the foundation for future exploration. It's a symbiotic relationship, complex and fragile, tying together ground and orbit in ways both practical and profound. And every day, astronauts aboard the station wake up, work, and sleep, knowing that home is always watching, always supporting, always just 100 kilometers away, yet impossibly far if something goes wrong. The view from above, an altered perspective. Ask any astronaut what they remember most about their time in space, and many will mention the view. Not as a cliche, but as a profound experience that changes how they see Earth, humanity, and their own place in the universe. From 400 kilometers up, Earth fills the windows. It's massive, brilliant, alive with color. Blue oceans, green forests, brown deserts, white ice caps. The atmosphere clings to the surface like a thin film, fragile and beautiful. During the day, sunlight illuminates continents in vivid detail. At night, cities glow like embers, tracing coastlines and river valleys with light. The ISS orbits with an inclination of 51.6 degrees, meaning it passes over most of Earth's populated regions. Astronauts see the Amazon rainforest, the Sahara, desert, the Himalayas, the Great Barrier Reef, the Atlantic and Pacific Oceans, major cities across 6 continents. Every 90 minutes, the view changes. New landscapes slide into view. Cloud formations shift. Storms develop and dissipate. Astronauts photograph these scenes obsessively, not just for scientific documentation, though Earth observation is a significant research area. They photograph because the view is overwhelming. It demands to be captured, shared, remembered. Some astronauts take thousands of photographs during their missions. The images are stunning, but astronauts often say they don't fully capture the experience. Seeing Earth with your own eyes, suspended in the black void, alive and vibrant, conveys something that photographs can't quite replicate. This experience has been described by many astronauts as the overview effect. The term, coined by author Frank White, refers to a cognitive shift that occurs when viewing Earth from space. Borders disappear. National divisions seem arbitrary. The atmosphere looks thin and vulnerable. The planet appears as a single, interconnected system rather than a collection of separate nations and continents. Many astronauts report that this perspective changes them. It's not mystical or vague. It's concrete. When you can see the entire Middle East in one glance, conflicts over narrow strips of land seem small. When you watch a hurricane form and track across an ocean, the power of natural forces feels humbling. When you see city lights illuminating the night, the human presence on Earth seems both impressive and fragile. Environmental concerns take on new urgency. Astronauts see deforestation in real time, patches of green turning brown as forests are cleared. They see glaciers shrinking, ice caps melting, coastlines eroding. They see air pollution hazing cities, particulates drifting hundreds of kilometers downwind. From orbit, environmental damage is visible and undeniable. Many astronauts become advocates for environmental protection after returning to Earth, driven by what they witnessed from above. The fragility of Earth's atmosphere is particularly striking. From the surface, the sky seems vast. From space, the atmosphere is a thin blue line, barely thicker than a pencil line, drawn along a globe. It's the only thing standing between life and the vacuum. It's all we have. And from orbit, it looks terrifyingly thin. Astronauts also see Earth's beauty in ways impossible from the ground. Auroras dance across polar skies, shimmering curtains of green, red, and purple caused by solar particles interacting with the magnetic field. From the surface, auroras are beautiful. From above, looking down at them, they're transcendent. Bioluminescent algae glow in ocean waters, creating swirls of blue-green light. Lightning storms flash beneath clouds, illuminating entire regions with each strike. Volcanic eruptions send ash plumes into the stratosphere. Rivers meander across floodplains in intricate patterns. Coral reefs shimmer in shallow waters. The ISS has a unique module dedicated to viewing, the cupola. Installed in 2010, it's a 7-window observatory attached to the Tranquility module. 6 trapezoidal windows surround a circular central window. Astronauts can float in the cupola, surrounded by views of Earth and space. It's used for operating robotic arms and observing incoming spacecraft, but it's also where astronauts go to simply look, to take in the view, to process the overwhelming experience of seeing their home planet from the outside. Some astronauts describe feeling homesick for Earth, even while they can see it constantly. The planet is right there, filling the windows, but they can't touch it. They can't feel wind or rain. They can't walk on grass or swim in the ocean. Seeing Earth so close, yet utterly unreachable, creates a strange, persistent longing. Others describe feeling protective. Earth looks vulnerable from space, a lone island of life in an infinite void. Seeing it like that, many astronauts report an almost parental urge to protect it, to preserve it, to ensure that this beautiful, fragile world survives. The view also emphasizes humanity's interconnectedness. Astronauts look down and see no borders, only landscapes. Political divisions are human inventions, invisible from space. The atmosphere flows across the entire planet, unconcerned with nationality. Oceans connect continents rather than separate them. Seeing Earth as a unified whole makes conflicts and divisions seem absurd. And then there's the rest of the universe. Looking away from Earth, astronauts see stars unobstructed by atmosphere. The sun blazes with fierce intensity, too bright to look at even briefly. The moon, when visible, appears stark and cratered, airless and dead. Venus and Jupiter shine as brilliant points. The Milky Way arches across the sky, a river of stars that's often washed out by light pollution on Earth, but stands out clearly in space. Yet for all the beauty of the cosmos, astronauts often say Earth remains the most captivating sight. It's the only world in view that's alive, the only one with color, the only one with dynamic, changing weather, the only one that's home. This altered perspective, the overview effect, doesn't fade quickly. Astronauts returning from the ISS often speak about their experience in terms of before and after. Before they saw Earth from space, and after. The view reshapes priorities, alters worldviews, and often redirects life trajectories. Some become environmentalists. Others enter public service. Many become educators, sharing their experience to inspire the next generation. The view from the ISS is more than scenery. It's a revelation, a mirror, a reminder. It shows us Earth as it really is, a small, beautiful, fragile world, suspended in an uncaring void, carrying all the life we know. And it suggests that maybe, if more people could see Earth from this perspective, we might treat it and each other a little better. That's the hope, anyway. That the view from 400 kilometers up can change how we think about the world 400 kilometers below. That seeing Earth from the outside might help us protect it from the inside. It's not a guarantee, but it's a possibility. And in a world full of division and destruction, possibility is worth holding on to. The future and legacy. What comes after the International Space Station will die deliberately. Sometime around 2030, possibly extended to 2032, the station will be deorbited. Thrusters will fire, slowing its orbital velocity. Atmospheric drag will pull it downward. As it descends, air resistance will increase. Heat will build up. The structure will begin to break apart. Most of it will burn up during re-entry, disintegrating into fragments that incinerate in the atmosphere. But some pieces, large modules, dense components, will survive the inferno. To ensure these don't impact populated areas, the station's final descent will be carefully controlled. Splashdown is planned for a remote region of the Pacific Ocean, far from shipping lanes or inhabited islands, a location known informally as the Spacecraft Cemetery, where decommissioned space stations and satellites have been laid to rest. It will end the same way Mir ended in 2001. Controlled, deliberate, observed from Earth by those who built it and those who lived aboard it. The ISS, humanity's most complex orbital structure, will streak across the sky one final time and then vanish beneath the waves. This decision isn't made lightly. The ISS has cost approximately $150 billion to build and operate. It's been home to over 270 astronauts from 23 countries. It's facilitated more than 4,000 scientific investigations. It's orbited Earth more than 157,000 times, covering a distance equivalent to traveling from Earth to Mars and back multiple times. But hardware ages. Modules launched in 1998 are now decades past their design life. Maintenance costs are rising. Systems are failing more frequently. Spare parts are harder to manufacture as original contractors go out of business or discontinue production. Keeping the ISS operational requires increasing investment for diminishing returns. More importantly, space agencies are shifting focus. NASA's Artemis program aims to return humans to the moon and establish a permanent lunar presence. The Lunar Gateway, a smaller station in lunar orbit, is under construction. Mars remains a long-term goal, though a crewed mission won't happen for at least another decade. These initiatives require resources currently devoted to the ISS. The plan is to transition low Earth orbit operations to commercial providers. Axiom Space is developing commercial modules that will initially attach to the ISS, forming a commercial section of the station. Eventually, these modules will detach and become an independent, free-flying station. Axiom Station aims to be operational by the late 2020s, providing a destination for private astronauts, corporate research, and international partners. Other companies are pursuing similar concepts. Blue Origin's Orbital Reef, a partnership with Sierra Space and Boeing, envisions a multi-user commercial station. Northrop Grumman is developing its own platform. NASA intends to become a customer rather than an operator, purchasing services from these commercial stations rather than building and maintaining its own. This model mirrors NASA's approach to cargo and crew transportation. After retiring the Space Shuttle, NASA funded commercial development of cargo and crew vehicles through SpaceX, Northrop Grumman, and Boeing. Today, those companies provide reliable, cost-effective services. NASA hopes to replicate that success with space stations. But the transition is uncertain. Commercial stations require customers beyond NASA. Space tourism, pharmaceutical research, manufacturing and microgravity, satellite servicing. These markets exist, but haven't yet proven they can sustain a large orbital infrastructure. If commercial demand doesn't materialize, the stations might struggle financially. If they fail, there could be a gap where the ISS is gone, but no replacement is operational. China is building its own station. Tiangong, meaning Heavenly Palace, is a modular station being assembled in orbit. It's smaller than the ISS, but demonstrates China's growing space capabilities. International partnerships are invited, though geopolitical tensions complicate collaboration. The recent record-breaking 9-hour spacewalk by Chinese astronauts shows that Tiangong is pushing operational boundaries, advancing spacewalking techniques and endurance. India has announced plans for its own space station by 2035. The United Arab Emirates is developing a lunar station concept. Private companies in multiple nations are proposing orbital habitats, research platforms, and manufacturing facilities. Low Earth orbit may become more crowded, not less, in the coming decades. But none of these replace what the ISS represents: genuine international cooperation. 5 space agencies, from nations that have been adversaries and allies, building something together, sharing costs, risks, and benefits. The ISS proves that such cooperation is possible, even in an era of increasing nationalism and competition. Whether that spirit of cooperation will endure is unclear. Space is increasingly commercialized and militarized. Nations view orbital capabilities through the lens of national security and economic advantage. The collaborative framework that enabled the ISS might not survive into the next generation of space stations. Yet, the ISS leaves a legacy beyond hardware. It provides 2 decades of operational experience in long-duration spaceflight. It taught us how to keep humans alive for months in microgravity. It refined life support systems, medical protocols, exercise regimes, psychological support. It demonstrated that recycling water and air to extreme efficiency is possible. It showed us the effects of space on the human body and suggested ways to mitigate them. That knowledge is invaluable. Without the ISS, plans for lunar bases or Mars missions would be far more speculative. We wouldn't know that bone loss is severe, but manageable. We wouldn't know that vision changes can be permanent. We wouldn't know that 98% water recycling is achievable. We wouldn't have tested technologies for years under actual space conditions. The ISS also inspired a generation. Children who watched astronauts floating aboard the station grew up to become engineers, scientists, and astronauts themselves. Public interest in space surged during dramatic moments. The first module launch, the first crew arrival, spectacular Earth photographs, emergency spacewalks, record-breaking missions. Astronauts who lived aboard the ISS often speak of it with affection. They call it home. They describe its quirks, its smells, its sounds with the familiarity of someone remembering an old house. It's not just a machine to them. It's a place they lived, worked, ate, slept, laughed, and sometimes cried. It's where they watched Earth spin below, where they conducted experiments that might help people, where they experienced something only a few hundred humans ever have. When the ISS finally deorbits, it will be mourning as well as closure. Something irreplaceable will be lost. Not just hardware, but a symbol of what humanity can achieve when we cooperate, rather than compete. When we focus on science and exploration, rather than conflict and division. And yet, endings allow beginnings. The ISS was always meant to be temporary. It's a stepping stone, not a destination. Its purpose was to teach us how to live in space so we can venture farther. And it has succeeded at that. The astronauts aboard the ISS right now, at this very moment as you read this, are part of that legacy. They conduct experiments, maintain systems, document their experiences, and prepare for the day when someone else will take their place. They're links in a chain stretching from the first humans in space to the first humans on Mars. They don't know how far that chain will extend, but they trust it won't break. Because here's the final, most important truth about the ISS. It proves we can do hard things. We can build structures in space. We can keep people alive in environments designed to kill them. We can cooperate across borders when motivated by a common goal. We can adapt, improvise, and persevere when things go wrong. The ISS is 420,000 kilograms of metal, glass, and electronics falling around Earth at 28,000 kilometers per hour, constantly dying a little each day from atmospheric drag, kept alive by human ingenuity and international cooperation. It's a marvel. It's fragile. It's temporary. But for over 2 decades, it's been home. A small outpost of humanity in an infinite void where people live, work, dream, and look out the tall windows at the beautiful, fragile planet they came from and will one day return to. The ISS will end, but the knowledge it provided, the inspiration it generated, and the proof it offered that humans can survive and thrive in space will endure. And perhaps that's the greatest legacy of all. Sleep well and dream of falling forever through a sky you'll never quite reach.